All right, AP Calc students, in this video, we're going to talk about how to interpret a derivative in terms of velocity and acceleration. So before we get into the differentiation, I want to bring up an important point about average velocity and average acceleration. When students are asked to find average velocity, you would use the difference quotient S of b minus S of a all over b minus a, where S is understood to be the position function. But oftentimes, students will do the change in velocity over the change in time inadvertently. But this, however, is going to give you the average acceleration. So just be careful. The average velocity formula is change in position over change in time. If the units are feet in second, then the units would be feet per second. Average acceleration is change in velocity over change in time, and the units would be feet per second, or feet per second squared. So a quick check of the units will help you understand if you did this correctly. Now let's get back to interpreting a derivative as velocity or acceleration. So suppose we have an object moving along a line with position function s, where s is a function of time, so f of t, and f is a twice differentiable function. The velocity and acceleration functions of the object are going to be as follows. V, or we could write it in function notation, v of t, is equal to the derivative of the position function with respect to time, which we could also note in function notation as f prime of t. Now, the acceleration, which we call a, could be written as a function a of t, and that's equal to the derivative of the velocity function with respect to time. But since velocity itself is a derivative, that can be thought of as the second derivative of the position function, which is also in function notation f double prime of t. So since the acceleration is the rate of change of velocity, we could say that the velocity of the object is increasing if a of t is greater than 0, and decreasing if a of t is less than 0. Let's look at an example here. The position of an object moving along the x-axis is modeled by the function x of t and is measured in kilometers, and t is measured in hours. We want to find the average velocity from t equals 2 to t equals 4. Average velocity is change in position over change in time. So that's going to be x of 4 minus x of 2 all over 4 minus 2. If we plug 4 into the x function, we get 0. And if you plug in 2, you get 8, which simplifies to negative 8 over 2, or negative 4. Now, the units on this would be kilometers per hour. It didn't ask us to interpret it, but we would say the average velocity of the object moving along the x-axis is negative 4 kilometers per hour from 2 to 4 hours. Now, if we want the velocity at t equals 3, the velocity is equal to the derivative of the position function, which is going to be, and then we plug in 3 for that into the velocity function, you would get negative 5. The units here would be kilometers per hour. And this would be interpreted as the velocity of the object at 3 hours is negative 5 kilometers per hour. Part C, we want to find the average acceleration, which is change in velocity over change in time. So it would be v of 4 minus v of 2 all over 4 minus 2. This would simplify to 4 over 2, or just 2. And since the units were velocity divided by time, it would be kilometers per hour, or kilometers per hour squared. And so the average acceleration from t equals 2 to 4 hours of the object is 2 kilometers per hour squared. And then the acceleration at t equals 3, you would have to get the acceleration function, which is the derivative of the velocity function. So that's going to be 6t minus 16. And then we plug in 3 to that. So 6 times 3 minus 16 is going to give you 2. And this means that the acceleration of the object at 3 hours is 2 kilometers per hour squared. Okay, we'll do another quick example involving a trig function. So part A, if we want to find the average velocity, that's going to be change in position. So x of pi over 2 minus x of 0 all over pi over 2 minus 0. So if we plug in pi over 2, the numerator is going to be pi over 2. It's going to simplify to that. And then the denominator is also pi over 2, so that's equal to 1. And the units here would be kilometers per hour. Part B, the velocity of the object. Again, derivative of the position function. We'd have to use the product rule here. So derivative of the first times the second plus the first times the derivative of the second. And then the derivative of the 3 is 0. So v of pi over 4, if you plug pi over 4 in, you'd have root 2 over 2 plus pi over 4. Cosine of pi over 4 is again root 2 over 2. And that's going to simplify to pi root 2 over 8 plus root 2 over 2. And again, the units on this would be meters per second. Part C, if we want the average acceleration, we would have to do the change in velocity over the change in time. And that's going to simplify to 1 over pi over 2, or 2 over pi kilometers per hour squared. And then part D, the acceleration function is equal to the derivative of the velocity function. So the derivative of sine is cosine, plus, got to do the product rule here, derivative of the first times the second, plus the first times the derivative of the second, and sine t is going to be subtracted. So this is going to be 2 cosine t minus t sine t. And then if we evaluate a of t at pi over 4, you're going to end up with root 2 minus pi root 2 over 8. The units there are going to be kilometers per hour squared. All right, that's interpreting a derivative using velocity and acceleration functions. Hope that was helpful to you. Please do leave a comment below. Let me know and subscribe to the channel and make sure you like the video.